This 2.5 in the book says we have a reinforced concrete beam with the cross section shown. It's on a simple span of 28 feet, carries a uniform service load, 3.6 kips per foot, live load, 2.2 kips per foot dead load. Check the adequacy with respect to moment. So first off, when they say check the adequacy with respect to moment, they're saying this. Is this beam's design capacity greater than or equal to the required capacity or required moment? All right? So there's two pieces to this problem. This is your standard evaluation problem. One piece is you got to find out what the required or the factored moment is that you got to compare the beam against. All right? This side is all about the beam, the design capacity. So it's based on how big the beam is, its width, its effective depth, how much steel it has in it, and so on and so forth. The design capacity side, we've talked about that last week. We'll talk about it again some more in a different light today. But in this case, what we can do is we can say, and we'll look at part A because part B has done the same thing. Part A says, hey, we're reinforced with 6 number 10 bars. Okay? So the first thing we do is the tension is equal to area steel times Fy. The area steel of 6 number 10 bars is what? 7.62, because you said I got 6 bars, so 6 times, and what's the area of a number 10? 1.27, I think. All right. So 7.62 square inches times, we're using 60 KSI steel, so the tension force, the tension result that this beam can generate is what? 304.8. That's kips. All right. T is equal to the compression force. So 304.8 kips is equal to 0.85 F prime C. F prime C. Oh, I made a mistake here. 40,000. Yeah. Sorry about that. They used to write 60 KSI. They said they switched this up. That's unusual.
It says PSI in the book, not KSI.
I'll work it, Joe.
304 is right.
304.8 is right. Okay. Sorry about that. 40 KSI steel is not going to be typical, but that's all right. So 304.8 kips is equal to 0.85. F prime C is, they say 3,000 PSI, but I'm working in kips, so I'm going to say 3 KSI. A times B, and the width of our beam is 20 inches. So I solve for A here, and A comes out to be what? 5.97. Anybody confirming this for me? Okay. All right, so then Mn is equal to T times the quantity of D minus A over 2, and the D that they give us here is 42 inches. A we just solved for. And I'm going to divide that by 12 just because this is inch. This will be inch kips. If I divide it by 12, this becomes foot kips. That's probably, you do it either way. I just like working in foot kips myself. Now again, that's Mn. We want phi Mn. We want design capacity. So design capacity, our resistance factor is always 0.9 for bending. So Multiply that by 991, what do we get?
892.
892. So my design capacity of this beam that's 20 inches wide and has an effective depth of 42 inches, 6 number 10 bars, is 892 foot cubes. All right? We got to compare that to MU. All right? Has anybody got any questions about this? Okay? All right. We've got to calculate MU. Now the first thing that we got to do is read the problem again. Because the problem says, hey, I've got this beam, it's 28 feet long, and it carries uniform loads, and they're service loads. Service means what? Unfactored. All right? So 3.6 kips per foot live load. What does a live load get multiplied by? 1.6. That's the typical load factor. 3.6 times 1.6 is what?
5.76.
5.76.
76.
Then dead load. They say it's 2.2 kips per foot. Dead load service. What does that get multiplied by? 1.2 is the load factor. So 2.2 times 1.2.
2.64.
2.64. Anything else we should remember? Yeah, self-weight. Again, you got to read the beginning parts of the problems, but it basically says unless they tell you self-weight's included, then you have to include self-weight. This problem statement doesn't say that self-weight's included in the dead load, so we're going to have to go ahead and put it in. And it's a relatively large beam too. So the beam, we'll call this SW for self-weight. The beam's 20 inches wide. The overall depth of the beam is 45 inches. I divide that by 144, put it into square feet. I multiply this by the density of concrete. You know, if you're in pounds per cubic foot, it's 150 pounds per cubic foot, but I'm working in kips, so I'm saying 0.15 kips per cubic foot. And then self-weight is a dead load again, so I'm multiplying it by the load factor.
So you said that's the volume of concrete?
This is area right here.
That's the area?
This is density.
Density, where do we find those numbers?
Where do we find what numbers?
The density.
Densities, that's a constant.
Okay.
That's always, it's either 150 pounds per cubic foot or 0.15 kips per cubic foot. What do we got here?
1.125.
1.125?
Mhm.
Now, again, realize what that's, we talked about this last week. I mean, concrete's a different animal than steel. That's saying that this beam, which, you know, it's fairly big, I mean, 20 inches by, you know, 45 inches, weighs over 1,100 pounds per foot, 1.1 kips per foot. You never saw a steel beam even approach, you know, quarter of that in all the stuff that you were doing. So, anyway, so we add up all these weights. They're all uniform loads. We'll add them all up. What do we come up with? 9.522 kips per foot. All right? So we've got this beam. It's 28 feet long. I've got a uniform load, 9.52 kips per foot on it. All right? And that's, you know, pretty easy free body diagram, it's pretty easy. Problem of actions. I mean, you know, the total load is just split to the left, to the right, half and half. What's the reaction?
133.
What was it?
133.
133.3. Okay. All right. Shear and moment diagram, really straightforward. Shear comes up to 133.3, goes down, back up, crosses out in the middle. Moment diagram, again, it's just simply the area under shear diagram. So it comes up, sort of a parabola, like that. That moment out there, that maximum moment is this area. So this area is 1/2 base, it's 14 feet, height, 133.3. 933. Again, look at the units, kip, foot kips, that's why we did the other one. Okay, so, back to the beginning. What was my design capacity? 892. What's the required moment or factor moment? So my evaluation says the beam is not okay. All right, that's it.
Is the book's 939, that 6 matter?
No.